Hello everyone, my name is Kazumi Chandrasiri and I will be presenting our research on contact point estimation along air tube based on acoustic sensing of pneumatic system noise. Silicon tubing or a pneumatic tube is a tough elastomer. Flexible but strong, the tubing is vital material across a broad range of industries. The material's resistance make it suitable for a lot of different devices such as water systems in the household, surgical drains in the medical field, shock absorbers in automobiles, and etc. In addition, they are an essential component for all pneumatic and hydraulic systems as fluidic pathways in the robotic sector as well. Here, I would like to explain the background behind this research. For the past decade or so, several research has been conducted on pneumatic tube sensing. Out of the many, tube sensing was accomplished by using pressure waves on the air inside the tube by John in 2009 and by emitting ultrasonic waves onto the tube by John in 2016 and by Tejara in 2019. However, pneumatic system is not addressed. Other research, such as a soft pneumatic actuator, has been performed using active and passive acoustics. For example, Zoller in 2018 used passive acoustics to sense the contact location, the contact force, and contact material in a soft pneumatic actuator. And also, in 2020, they used active acoustics for contact sensing in soft pneumatic actuators. Also, length estimation using pneumatic active acoustic sensing has been performed by Takaki in 2019 for soft pneumatic actuators. Therefore, in our research, the aim is to create a versatile contact sensing technology for pneumatic tubes in pneumatic systems. To be even more specific, contact point estimation on tubes. Let me take you through the results of our proposed method. We were able to estimate the contact position in an air tube using active acoustic sensing. As you can see in this video, the locations or positions taped in red, yellow, and green are estimated accurately under two different air pressures. As you might have noticed in the video as well, we use the noise generated by the air pump in this entire system as our active acoustic sound source without using any external sound emitting device. And the pneumatic noise propagates through the air tube, which is reserved for the soft pneumatic actuator. We use the simpler system configuration for acoustic sensing. This consists of pneumatic tubes, a control board to control the air pressure inside the tube, a soft pneumatic actuator at the close end of the tube, which completes our pneumatic system. And also, most importantly, our sensing device, which is a contact microphone attached to the tube, encased by a 3D printed component. Let me move on to the methodology. This briefly depicts the flow of our research. First, we acquire the pneumatic noise propagated through the tube, and we pre-process this data, and this outcome is used as our input for the machine learning model based on convolutional neural networks for estimation. At the pre-processing stage, the pneumatic noise acquired by the microphone is amplified by 40 decibels. And this amplified noise is short-time Fourier transformed in order to create amplitude spectrums of frame shift 50 milliseconds. And these amplitude spectrums are used to obtain spectrograms of length 1000 milliseconds and 300 by 20 pixels of resolution. Before moving on to the main experiments, we confirm the feasibility of using pneumatic noise for tube sensing. The first figure here shows the spectrogram when the tube is untouched. As you can see here, the pneumatic noise is about 600 Hertz of frequency. And then the second spectrogram is when the tube is touched or with contact. And here, as you can see, there are a few color changes or glitches in the spectrogram, which shows that there are characteristics in the frequency domain when contact is made on the tube. So based on the VGG16 architecture by Simonian in 2014, we created a simpler model that has 4 convolutional layers, 2 max Boolean layers, and they extend to 3 fully connected layers. Next, I would like to present the evaluation of our proposed method. We performed 6 evaluative experiments as listed here by estimating contact on split air tube, varying air pressure, tube length, contact point resolution, changing the machine learning techniques, and lastly, on a pneumatic system with multiple air channels. Each of these experiments will be described in the next few slides separately. We performed experiments on a split air tube by varying the microphone location on the tube between the air pump and the regulator, and then between the regulator and the soft pneumatic actuator. A and B shows the 2 layouts. The air pressure is varied during data acquisition process. And we used an air tube of 500 millimeter length, which has 1 to 9 contact locations, and 0 we labeled as the non-contact. The data was recorded for 31 seconds per each contact and non-contact location alike, and 600 spectrograms per scenario was obtained for training. We then used 5-fold cross validation for our evaluations. The results are shown in these confusion matrices. The confusion matrix on the left here shows when the microphone is attached between the pump and the regulator, and the confusion matrix on the right shows when the microphone was attached between the regulator and the soft pneumatic actuator. The recognition rate was approximately 97%, which shows that the device location and the split air tube does not greatly affect the recognition rate. Our next evaluation was done by varying the pressure inside the tube. The length of the tube and the number of contact locations were same as the previous experiments. And so we tried to create our estimation model using data obtained at 1 pressure, which is 0 kilopascals. And then we tested this created model with a different set of data obtained at 41.3 kilopascals. So as you can see in this confusion matrix, if you train the model with just 1 pressure varied data, the estimation is actually not good. Therefore, we believe that our method that we have been using in the previous experiment as well, varying air pressure data, is a requirement for a better model. So we have employed that methodology throughout our evaluation and other experiments. So it is also necessary to consider the variation of the tube length when it comes to different applications. So since we have checked the pressure, in this experiment, we kept the pressure to just 1 pressure level, and we incremented the length of the tube by 5 meters. The data acquisition is, the process is the same as that of the previous experiments. And here we observed that there was no drop in estimation accuracy with varied length. So we understood that pneumatic noise can propagate long distances because of its low frequency. In previous experiments 1 and 2, the contact position resolution was kept to 50 millimeters. However, in practical situations, the contact resolution could be much denser. Therefore, in this evaluation, we varied the resolution to 25 millimeter gap between the contact positions on a 500 millimeter air tube. The air pressure was fixed on 1 value, and the data acquisition process remained the same as of previous experiments. The recognition rate was about 93%, which shows that our proposed method has the ability to detect a high density of contact points. Then also a model based on CNN, like in our methodology, would require a large amount of training data, which means higher density of contact point data are required. However, we considered a situation where the amount of data is low and a simpler machine learning technique, depending on the application, needs to be employed. For this situation, we created a simple neural network model and used power spectrum of one dimension as our input data. The recognition rate was approximately 86%. So even though we cannot for sure say that this estimation rate is high, depending on the application, we could conclude that this estimation accuracy is acceptable and that a simple machine learning technique can be used in this proposed method for estimation. Lastly, we conducted experiments to check the feasibility of our proposed method on a pneumatic system with multiple air channels. We divided the main air path to 3 air paths labeled A, B, and C. The microphone was attached to the main air path. So here, the estimation accuracies for all 3 was over 90%, showing that the estimation of multiple air channels is possible by our proposed method. And we applied our method on an application. We employed a soft gripper to demonstrate a user interface using contact point estimation. The gripper closes by contact, which means air is fed into the tube, and without contact, it opens. So we tried grasping 5 different objects, and as shown in this video, a box cutter, a flathead screwdriver, and also we tried a remote controller, a wallet, and a squeaky hammer. So the maximum weight we tried was 245 grams. So that is the end of our evaluations on this proposed method. So moving on to discussions and limitations. As you all know, the frequency of pneumatic noise is lower than that of ultrasonic sound. That means the attenuation of this propagated vibration is also low. Therefore, we can conclude that pneumatic noise travels a long way along the air tube. So as of this moment, we have not confirmed the maximum length possible for the propagation. In our evaluation experiment, if you have noticed, we used a 16-meter tube as our maximum length, but that was only because we had a 16-meter tube when we did the experiment and we didn't have a much longer tube. Therefore, we have to explore the maximum length of air tube in the future. As for the limitation, we believe that the annotation for training data in this research was a limitation. Our data acquisition process is not fully automated, so it takes a lot of time to obtain larger data sets. Also, if the system configuration changes from an electric air pump, for example, to a carbon dioxide cylinder or an intermediate air tank, our proposed method would not work, because a carbon dioxide cylinder or an air tank would not produce any noise that we can use as our active acoustic sensing technique. And also for then to about the material of the tube, a harder tube is better than a soft tube because the pneumatic noise propagates through the surface. Therefore, harder the material, better the propagation is. So if you use a very soft tube, the estimation accuracy could actually be a bit lower. So, but depending on the application, you can actually choose the toughness of the tube. So if the tube is medium hard or very hard, this method works really well. And this is a conclusion and summary of our research. So we estimated the contact points using pneumatic system noise under various experimental conditions. The overall recognition rate was about 98%, considering all the evaluations that we did. And we confirmed the method by implementing it on a robotic gripper to grasp several objects. As for our future works, we would like to work on a robotic system for the data acquisition process to make it automated so that it will require less time for us to actually perform the experiments. Thank you so much for listening to this presentation. If you have any questions, please direct them to us on this email address reading below. Thank you.